so that you can study here in class. Our TA, Anna, is up here in the front row. And if you want to come and sit left or right side of her, perfectly fine. Sit in this chair, please. And Miss Yasmin, our SI leader, if you want to come up, there's a seat on either side of Yaz, and there's a seat on either side of, says total 4 students. If you feel like you want to come up and study up here with them during class and just get, help you with your clicker or help you with any calculations and stuff, you're more than welcome. And many students do that. Question? Can you go to SI if you have a specific question, or can you just go and participate? Yes, go ahead and answer that. Yeah, she just go. It's going to be like mental osmosis, So, and you might make some friends and study partners and stuff like that, So it's, so if you can make it, it's definitely worth going to. Here's the SI schedule. Speaking of, so our next one is Monday. And how did it go this morning? Well, good. All right, good. Now we're going to have some homework. You might have noticed on the previous slide that we're going to have homework too. Finally, I finally got around to satisfying myself that you guys are ready for it. But now let's get to what's happening today, and we'll just recap a little bit from last time. Now we had this formula, delta x, changing the x coordinate, equal to vi, the initial speed, times the time, plus 1/2 at squared, and a stands for the acceleration. So for some interval of time t, so t could be 2.1 seconds or 0.23 milliseconds or something like that. If you want to figure out the position, you would use this formula. Now, the thing that we talked about last time was that if you drop something, if you're thinking now instead of horizontal x coordinate, if you're thinking y coordinates, and if you drop it from rest, so you're up at the top of the library and you've got some water balloons and you just want to drop them on somebody as they come out of the library, right? And don't deny that you would love to do that, because I remember when I was in college, all those many moons ago, I actually, we beamed a guy that we didn't know he was a professor. He was a visiting assistant professor of psychology, and we got him at long range, like about 100 yards. We had this slingshot that we had. It was perfectly coordinated for water balloons, and we nabbed him right in the back, and he got soaked. And boy, did he get mad! He came charging up to the 4th floor of the dorm, and I remember, and we were doing all this from up on the balcony. So to get away from this guy, I climbed up on the roof. I just waited up there on the roof while this guy, boy, was he, I'll never forget it. So try not to get any psychology props. They're a little touchy. But at any rate, if you're dropping it, you're not using like us juvenile delinquents, you're not using a slingshot, then this term here, it's the first part, v subscript I, that's 0 if you're dropping it from rest. So you don't even have to write that in. And that allows for a really nice simplification. Just simply figuring out the drop distance. This is what I call the drop distance formula. All right. Now, if you're trying to figure out y coordinates, x coordinates, and where it is in space, then you have to use minus signs and stuff. But this one, just use g equals positive 9.8 meters per second squared, and you can get the drop distance. Just time it, and then calculate this one mentally. And we're going to work on how to do that. So you just go 1/2 times 9.8 times the square of whatever time interval you've got. All right. Now we're going to do Make sure you have this formula written down. D equals 1 half gt squared. The drop distance formula. It's a distance triangle formula. 1 half base times side on a velocity graph. But we're going to do an example now. As you might remember from the movie The Lord of the Rings, the Mines of Moria. Here's the Mines of Moria. We're going to do a calculation. So turn on your clicker. It's going to be a numeric answer. And so let me change the question here to numeric. And so hit your refresh key and you'll get numbers to start with. And here we go. You drop a rock down a well like Peregrine took, and you hear a splash 3.2 seconds later. How deep is the well in the Mines of Moria? Okay, so type in the numeric part of your answer to the nearest 0.01 meters, and then type that in. So for instance, 22.31, and then hit the send key. All right, and as always, definitely if you're sitting next to somebody, go ahead and talk with them, and consult, see what they got, see if they have what you got, or come up here and sit with Yaz, or talk to Yaz over her shoulder, or up here in the front with Anna. That way you can always get your clicker calculations correct. And by the way, try to get yourself a good calculator. The exam is coming up, so we got to get that done. And we got to have a regular calculator for exams and stuff, because you can't use your cell phone. Now I'm gonna make a public service announcement here for anybody here that's a psych major. Go up to the psych office sometime this week and tell them to fill up the soda pop machines in the ground floor here. It's ticking me off. They don't have any water. They don't even have any vitamin water. So take your time, consult, double check. Question? Yeah, that's what we want. We want numeric. So all you want is a number, something, something, point, something, something. All right, so here. Yeah, so you're on one now, so just use the up and down arrows and the right arrow key. And G is not zero, it's a 9.8. 9.8 meters per second squared. That's the acceleration due to gravity. We got it from Galileo. He's the one that first measured it. Yep. All right, good. You guys are doing good. Let's see what your answers are. Uh-huh. Round off carefully, please. Something, something, point, something, something. I see some something, something, point, something. And I see something, something without any decimals. And don't forget to hit the send key. I see 100 of you have answered. Very good. Raise your hand if you've answered already. Good. Raise your hand if you're still working on it. Okay. Good. No problem. Take your time. And I'll go over this calculation with you in case you get, and it's tripped up a few of you, but we'll just go over it nice and slow. Nice and easy, step by step. Frequency. Frequency 1.5 megawatts. Yeah. If it's free fall on the surface of the Earth, G is negative 9.8 meters per second squared. And in this one, you don't even need the minus sign because you already know you're going downwards. So. If you were trying to write an equation, you would put the minus sign in if you were trying to write a y coordinate, like y equals negative 2.5 meters. So that would be if you're up on top of the library, and you say, okay, let's call this y equals 0, and then x equals, the x-axis and the y-axis right there at the edge of the roof. Then the top of the roof is y equals 0, and then negative 2.5 would be, 2.5 meters below that. So like down on the 5th floor somewhere. All right, so that's how you would use that. But in this case, you're just figuring out how far down is it. So it's basically, you don't need the minus sign on this. All right, 20 seconds starting right now. Ten, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Okay. And the answer is raise your hand if you have 50.18 meters. Nice. That's about 165 feet. And I see a few of you have 50 point something. You didn't round off quite right. But let's take a look at how to calculate that now. All right. So here's your formula. So go ahead and jot this down. Even if you got it right, you might want to copy down my technique. All right. So there's the drop distance formula. We're not trying to get a y. You can sit up here if you want. Stay up here. Yeah. Okay. We're just trying to figure out how far something drops, okay? So you plug in the numbers that you have, 0.5, let me get it over here. I better turn half around here. 0.5, okay, so that's 1/2, and then here's the value of G, 9.8 meters per second squared, and you don't need the minus sign for this one, because we're just getting a distance, not a coordinate. And then here's the drop time, 3.2 seconds, quantity squared. Now you got to square that. Okay, so 3.2 squared. So what I normally do is, okay, 0.5 times 9.8. That's good old 4.9. Okay, so that's my first parentheses. And then my square of the bracket up here, 3.2 seconds, quantity squared, that's the same as 10.24 seconds squared. All right. And the square is now inside the bracket, and it applies to the unit of seconds. So this is square seconds, which is kind of weird, but it's going to cancel out. Because look, top and bottom here, in the 4.9, you have seconds squared in the denominator here. You see that? Look at that. Don't look at your notes. Look up here. Look at my cursor. Come on, look at my, there we go. Good. Look at that. Meters per second squared down in the denominator here. So that cancels this second squared up here in the numerator. But we're still left with meters. Okay, that didn't get canceled out. And that's good because that's what we want. We don't want that one to cancel out. So this one works out nicely. 50.176. And then you got to figure out, okay, I better round it off to whatever Dr. B says. And I want it to the nearest 0.01 meters. So that means 50.18. And that's how you do it. Now let me pause for questions. Yes. No, no. You have to use some discrimination. You have to read carefully. And as I've said, if you're trying to figure out why a y coordinate in a coordinate system like on XY graph paper, then you'll need the minus sign. But this is not an equation. We used the coordinate equation to get this, but this is just a drop distance formula. So a distance is always positive, okay? And this one is just saying how far is it going to drop, and it doesn't really make a reference directly to a x and y coordinate system. But if you do make a reference to that, and we'll have some problems probably on homework next week, where you have to actually calculate a y coordinate, it might turn out to be negative 2.7 meters, then you'll be using it. And so you have to read carefully and kind of make a decision. If it's about a distance, positive values only, just use positive 9.8. If it's about a coordinate, where on a piece of graph paper, then you have to use the minus sign, because that indicates downward on the coordinate system. All right. Now, let's put together Galileo's formula for the y coordinate. And this is, what is your name again? Brad. Okay, Brad Meister, this is where you would use the negative 9.8 in what we're about to do. Okay. All right. So this is the first half of your arc. Okay, so you hit a baseball towards the outfield and so forth. And you have a final height, y subscript f, or final y coordinate. And you have your initial. So it starts down here at y subscript I. That's the field level down here. And it gets as high as, so this is your drone up here. So you throw the ball up to your drone and it do they make Nerfs that are sticky? Like Nerf balls that are sticky? Okay, so this is like a sticky Nerf ball. It sticks to the drone and stops. Okay, right at the top of its arc. Okay, and so that's y subscript f. All right, so, and notice here, Brad, I have graph paper here in the background, right? So that means, yeah, we want to, worry about positive and negative. Now this one's going to have positive value for y subscript f, and it's going to have a 0 value for y subscript I. That's all right. We're still going to use that minus sign in there, just in the event. All right. So here we go. We start with the initial y coordinate, and if you don't do anything, if you don't throw the ball, if there's no gravity, that's all you got. It's just kind of sitting there in your pocket or in your mitt. It's in your gear bag. You get to the field and you're just kind of waiting for the drone guy to come. Now, then you throw it. Now you throw it with a little bit of forward speed and a little bit of upward speed. So that means it's going to go up like this instead of straight across the field. Okay? And you're not throwing it straight up, but you do have some upward speed and you have some sideways speed to get this kind of an arc. So as far as the y coordinate, you have to look at the vertical component of the initial throw speed. Okay, so VI, initial velocity, and then subscript y means the y part of it, the vertical part of it. Okay, so if you're 45 degrees tilt angle for your throw, then you have the same number of meters per second vertically as horizontally. You know, if you have a steeper angle, that means you have a little bit more vertically than you have horizontally. Okay. Now, if there's no gravity, this is where it would go after time t. But we have gravity, and so we've got to put in the 1/2 gt squared. And in this one, Brad, now you use the minus 9.8 meters per second squared, because this is asking about y subscript f, a y coordinate, somewhere on the arc, in this case at the top of the arc, where the drone is. All right? It must be raining hard. I'm going to get soaked. Can you hear that? Oh my goodness. Now, what was I talking about? Oh yeah. So where this object would go is yi plus viy times t if there were no gravity. But the gravity, so this thing would go a little bit higher if there weren't any gravity. It would just keep going, you know, just these first two terms. You have this and this. So if you're somewhere, you're playing in space, and at your baseball field there's no gravity, you know, everything's a home run, I guess. But if you have gravity, you have this term. And notice this one is going to be negative because there's a negative in the g value. So it's a negative 9.8. And then 1/2 is positive. And t squared is positive. So positive times negative is negative. All right? So this is taken away. So when I say you're not going to go as high, that's what it means. So this is where you'd go if there was no gravity. And then this is the effect of gravity, which means, you ain't going that far. In fact, you're going to curve down to an intermediate altitude, y subscript f, according to this formula. All right? Now, let me remind you also of another concept that we've talked about, the distance rectangle, the distance polygons. We did some distance trapezoids last time. Yeah, the distance rectangle, this middle term, VIY times t, that's a distance rectangle. All right? If that's all you had, if there were no acceleration due to gravity, if you were out in space playing baseball, then this is all you'd have. And that thing would just keep on going. It wouldn't curve back down towards the earth. It would just keep going out, you know, monster home run. Every hit would be a home run. All right? And this part over here, 1/2 gt squared, is a distance triangle. Now, sketch it out the way I have it. It's a distance triangle where the velocity graph is dipping down below the time axis. All right? That means that the change in the y coordinate from the distance triangle here is negatory, which I've just been saying. You know, you're losing distance that you would otherwise have. You know, so if all you had is, if you had no gravity and just VIY times t, everything's a home run. So that would be a long, nobody would ever, well, you could strike people out, I guess. So unless you had a really good pitcher with a good heater, everything's going to be a home run. So it's a long game. But with gravity, you know, things curve back down towards the ground, as you see in this diagram. So that's a distance triangle. And this is an upside down one. It contributes negatively because g is negative. All right. Now let me pause for questions. Yes, Brad. Right. Mm-hmm. Yeah, because this is the most general form of it. So you'd always use it. And you know, you could you know, You could mentally do arithmetic with positive 9.8 as long as you remember that it gets subtracted in this equation. So,
Just for the sake of the quiz and everything else, would we just be expected just to,
yeah, whenever you see the word distance or drop or from rest, 1 half GT squared, use 9.8 positive. Whenever you see, I want you to give me some X and Y coordinate. I mean, this is half the task, the Y coordinate. The other task is the X coordinate. If I ask you for some X and Y positions, think not negative 9.8. And unfortunately, we're going to have to, there's other things where we need to use the negative 9.8. And Andrew, I'll try to make it as clear as I can as I go, as I've been trying to do today. Okay. And anything where you care about a direction. Distance doesn't care about directions. It just cares how many you got. Kind of like a speedometer. It doesn't care what direction you go. It just cares, you know, how many miles per hour, whether you're going north, south, east, or west. And distance is the same way. But position means, X, Y, and Z, and, northwest, or, something like that. So then you got to worry about the negative signs. All right. But I'll try to make these things, I'll try to give you enough tip-offs in the question. So that's why I say drop, distance, stuff like how far. Here's another one, how fast. How fast is always asking about how many meters per second, not about direction. If I ask about a velocity, then I'm asking about a speed and a direction. All right. So we'll get used to it. We'll have some more homework before the exam, first exam stuff. So you can practice up on this stuff. Now, next topic for today that I want to talk about is Professor Galileo and his big kind of retroactive argument with his mentor. When Galileo was in school, he studied the books of Aristotle. They all did. It was Galileo who basically invented physical science as apart from the works of Aristotle. Now, people still study Aristotle to this day, but not for science. I mean, you could study it for background and stuff. And some of his biology, I guess, is useful. But in terms of his theories of motion, it's just interesting history, but not, but Galileo's got the right idea. So this controversy between these two great guys, and Galileo, everybody always thinks Galileo was against Aristotle. He wasn't. He valued Aristotle. He studied Aristotle when he was coming up as an undergraduate, but he had a difference of opinion, and he was able to prove it. And so this image of driving a car off a cliff, we're going to be using that today in this discussion. Also, I'd like to point out to you that all of chapter 2 is about this conflict and this big question answered by Galileo, posed and answered by Galileo. So here's one. And this is the question. Is there a state of motion between accelerated states? And Galileo was able to say, yes, there is. I also have this dialogue about the states of motion that you can look at and read. And it's me, I made it up. It's not from, Galileo wrote dialogues as well. And it's actually kind of a cool way of discussing concepts. So I have a little short one in there. But let's think about that Ferrari driving off a cliff. Okay. And here's a diagram from chapter 2. And sorry, I can't put a page number because the ebook version doesn't have page numbers. So, but it's in there, chapter 2. So the argument between Aristotle and Galileo about motion is basically about Aristotle's view versus Galileo's. Aristotle said that every motion requires a mover. And in other words, all motion is from a force of some kind. So when Aristotle was trying to describe an arrow flying through the air, he had to come up with an explanation as to how there was a force behind the arrow pushing it forward through the air. Now we don't use that today. We now know that you set the arrow in motion and it will go, and it'll maybe have a little bit of air resistance. But if you're on the moon where there is no atmosphere, no air resistance, an arrow will just keep on going, and eventually it'll curve back down to Earth due to gravity, but not due to a push force from behind it. Okay, so that was what Aristotle's view was. And it's not, we always think about Aristotle as benighted and stuff, that he was, like, how could he think that? What an idiot and stuff. And people give him a bad reputation, but he was smart. And it's not implausible what he thought, that everything moves because there's a force behind it. Because look, is your car going to just, you get it up to 60 and then you turn off the engine? No. You're heading to Miami, to watch the Miami Heat. I know you're not going to go to watch the Miami Dolphins, but maybe you're going down to watch the Miami Heat. And, you're on the turnpike and you get up to 70 or whatnot, and you don't turn off the engine and just say, okay, I'm done. Let me just coast all the way. No, it's plausible that you have to keep the pedal on the metal. Now, if you got cruise control, the car will do all that. You won't have to put your foot on it. But theoretically, Aristotle was thinking, yeah, man, I got to have cruise control of some kind. I can't turn off the engine. Whenever I go to Miami, that's what I got to do. So that's what he said. And Aristotle's view was it was justifiable. But Galileo, the real thing here is that Galileo boosted it to a whole new level. That's where the difference is. He wasn't really gainsaying Galileo. He was saying there's more to this motion than what you've got. And let's take a look at Galileo's view now. Okay. He said, yes, there are forced motions in nature, and everybody knows that. A horse pulls a wagon back in Galileo's day. The wind propels a sailboat across the ocean. But he said there are unforced motions which do not accelerate. Aristotle said, even if something's not accelerating, it has to have something pushing it. He said, if something's at constant speed, that's fine, but it has a push. And Galileo said, oh no, not necessarily so. A state in which the object doesn't slow down or speed up, all right, it's speed, it's the speedometer just reads 27 miles per hour, nice and steady. Aristotle would have said, yeah, okay, 27 miles per hour, nice and steady, but I still have to have the engine on. But Galileo said, well, what if you can idealize and think of it like a frictionless environment? Because that's what slows down a car. You turn off the engine, you're going to coast for a while, but friction's going to get you, and it'll roll you to a stop. But Galileo said, think of a Ferrari driving off a cliff, a hypothetical frictionless horizontal plane. So here's the idealization that Galileo conceived of. All right. And really, Aristotle could have done this if he'd taken a notion to it. But I don't know why Galileo thought of this, but he did. And I've studied Galileo quite a bit. But I can't think of how he came up with this idea. So on this horizontal, okay, so it's horizontal. So that means it's not a ramp, it's just nice and flat, so gravity's not doing jack, okay? And it's frictionless. So if you get something going, if you push something up there and then let go of it, it'll just keep on going at that speed where you push it off. So it's indifferent to being at rest or in motion. It doesn't really care, all right, on this hypothetical frictionless surface. If it's in motion, it'll persist at constant velocity until it leaves the plane, and then it goes over the cliff. All right. So, but until it goes over the cliff, you're just la 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 la, 26 miles an hour all the way till you reach the edge of the cliff, and then help, you're over the cliff in your Ferrari like they do in movies. And that at that point, then you have a forced motion due to gravity. Okay, and which Galileo knew all about that from his experiments on the Tower of Pisa and stuff like that. He did a lot of thinking and experimenting and measuring with that. And so Galileo, the thing that he did, and which is really how he didn't really dethrone Aristotle, but he made himself into the boss of Aristotle's, really, and became the head of our school. We're all in Galileo's school of science now. All you guys are students in his school. Isn't that kind of cool? 400 years old, 400 year school. You're in a long line. What a tradition. And you're all here voluntarily. And everybody, nobody's in here. Nobody's forced to be here, right? Everybody here is, well, not counting your parents. But everybody's here, voluntarily in the School of Galileo. He's the dean. I'm his student too. So is Sir Isaac Newton. So let's look at what he proved. Okay, and his proof, we can start with this view of it, and this is going into the dialogue. So I'm kind of talking about the stuff that is discussed in the dialogue in the textbook. So you're assisting Aristotle, okay, and you say that an object will move along the horizontal plane only if it experiences a certain amount of push force. Okay, that's what I was saying. That's what Aristotle's view was. He said, okay, frictionless plane, nice, but I still need a push force to keep it going. Okay, and Galileo's position was not really. And here's how he proved that not really is the correct view. All right, so here's a picture of a car on a frictionless horizontal plane. Speed is constant. And Aristotle says you need a bit of push force. So let's just say that it's 0.02 metric units of force. All right? Just for the sake of conversation. All right? So here's your car up here. And here's the little push force, P. Okay, that little black arrow up there. And so Aristotle says, yeah, about 0.02 ought to do it. And Galileo says, okay, nice, that's fine, nice, lovely. But it has some weight, doesn't it? This object has some weight? And of course, the answer to that is yes. But if it has, and Galileo said, well, let's say that this is a fairly smallish car, and its weight force is only 0.100 metric units of force. Now, that's 5 times the push force. Okay, so the ratio is 5 to 1, 1 to 5. Okay, so Galileo says, okay, and let's make this car fairly small. So I have a fairly small gravitational force. And Aristotle said, okay, good, it's got weight force, gravity's downward. Yeah, okay, nice. Weight force. What does that have to do with anything? And this is where Galileo turned the tables on him. He said, let's make a copy of the push force arrow. All right. Now look at this animation. This is me kind of animating my way through this. Copy the push force and the weight force arrow. All right. And then take them over here. Here they are. All right. Side by side. All right. And now tilt the weight force arrow so that it forms the hypotenuse of a triangle, a right triangle. There it is. Okay. And here's the right triangle we're talking about. See that? The red one? Okay. Now let me back it away a little bit. All right. And Galileo said, all right, your contention is a ratio of 5 to 1. Okay. And he said, look, if you take a ramp that's 5 to 1, in other words, it's 5 units of length on the hypotenuse and 1 unit of height on the vertical part, then he said, if you do that, the amount of gravity on that ramp is proportional to gravity in exactly the same proportions as the triangle itself. So what that means is the force down the ramp is exactly 0.02 metric units. So if the gravitational force is 0.10, the force down the ramp. So if this is a pretty shallow ramp. It's not very steep. Okay. If you're, a little old granny, the little old lady from Pasadena could walk up this ramp probably pretty easily. All right. 1 to 5. All right. And Galileo says, look, gravity is going to still force things down that ramp. You put a little marble up there and it'll roll down because there's a little force of gravity. Now, not much. The steeper you go, the more force you get from gravity. But at least you got this much. And this triangle here, let me turn around here. This triangle here is the 2 black arrows. Those are in the ratio of 5 to 1. And so is this ramp that you built, 5 to 1. And Galileo is saying 0.02 units of force is what a ramp uses for the speed. That's way more than what a flat surface would take. So Galileo says, look, you're way off. You're way overestimating a flat. No matter what you have, a flat ramp, just a flat frictional surface, definitely is going to be less than 0.02. I mean, for a car of this size, 0.02 is way more than you need. So even if I say, Galileo, yeah, okay, so it's not going to be 0.02. Maybe we should make it smaller. So Galileo thinks, okay, well, it is a car and I'm left-handed, so let me change and it's sunny out today, so let me change my view to 0.002. And of course there, Galileo would set up a ramp that is in a ratio 50 to 1. Okay, 1 unit of vertical and 50 units of ramp. And he's got Aristotle again. Change it to 0.0002. You can make a ramp for that. You can make a ramp for any of these things that will always contradict Aristotle. So what Galileo showed was Aristotle is wrong. The only possible value for the push force that keeps something going on the horizontal frictionless plane is zip zap, 0. That's because you can always build a ramp to contradict Aristotle or his assistant. No matter how small they keep it awake now, how small they make that force, or they imagine that force to be, Galileo can build a ramp, and you're basically busted. All right, so Aristotle was defeated. Now the problem that Galileo had with all of this in his day was that there were so many other guys, philosophers that had studied Aristotle, and boy, they didn't give Galileo a dime's worth of credence. They said, "Oh, Galileo, you're from Italy. What do you know? Pizza's good, but forget about it. And they're from all over Europe and all over Greece and stuff like that, Asia Minor, and they're all thinking Galileo, it's nice, but no, not really. And that's where he had his problems. If Aristotle had been alive in that day, Aristotle would have said, "Good for you, my wonderful student." But he wasn't around. It was only his students from Galileo's day that gave him a lot of trouble. Although he had other people that gave him credence. I have to say that as well. It was controversial. He was a controversial figure. Definitely a controversialist. Now, that frictionless state, that imaginary frictionless plane, a lot of times what we do is we call that the inertial state. And it's basically this: an object with no forces acting on it, or with no unbalanced forces acting on it, will stay in a state of motion, either constant speed, in other words, constant speed and constant direction. Okay? And that's Galileo's principle of inertia. All right? If you have no forces, like out in space, far, far away, or if you have balanced forces, like this clicker sitting on the tabletop up here. See this clicker right here? Okay, it's just basically, and there's forces on it, but it's not moving anywhere. It's at rest. But it's and if this were a frictionless surface here, I could slide it all the way off to the edge, and it would be at constant speed, because the vertical upward force from this table, this rigid table, and the downward force of gravity cancel. They're not absent. They just cancel. They're equal and opposite sizes. Okay. So now, Galileo's principle of inertia. This actually became Sir Isaac Newton's first law of motion, the principle of inertia, or the law of inertia. And so let's talk about, and now this is going into chapter 3. All right, we're going to now talk about Newton's laws of motion, dynamics. And if you read his book, well, his book was written in Latin, which I can't read, but if you read his translation into English, you'll find this sentence: every object retains its state of rest, or the state of uniform straight line motion, unless acted upon by an unbalanced force. Okay, now notice there it says unbalanced. So what that implies is that if the forces are balanced, like two vertical forces that balance, then you're still, uniform straight line motion. So that means constant velocity and constant direction. All right. So an example: an apple in an apple tree. Sir Isaac Newton was famous for apples in apple trees. Right? So these apples here on this limb, they have a pair of forces that balance. Okay, let's think about what those forces are. So there's the stem attached to the branch, and that pulls the apple upward, right? And then the gravitational weight force pulls it downward. And so the stem, has enough grip and enough toughness to hold the apple attached to the limb. All right? And then there's forces that keep the limb up and stuff like that. But if you just think about the apple, it's got some upward force from the stem attached to the branch, and of course some downward force from gravity. All right? Now, if it's at rest, then those forces balance. But if they go out of balance, For instance, if the stem dries out and gets brittle and weakens, then the balance will fail because gravity doesn't weaken. It's pretty constant. So if the stem force weakens, it can't deliver enough, eventually it's going to snap. Okay? And down it goes. All right? And then it hits Sir Isaac Newton on the head, and he thinks of the law of gravity. Or so the legend has it. All right? So that's an example of balanced forces in a state of rest. Now, I want to give you an example of, let me pause for questions here. Okay, let's keep going. Here's some examples riding in a bus. Now, this is for an object in motion. Okay. Now, if you're in a bus and like the UCF shuttle bus, okay, and it's going a constant 5 miles an hour south, for instance. It's heading from the physics building down towards the research park. So it's going south, okay, 5 miles an hour. And there's no, you're on board the bus, you're standing in the aisle, no problem, okay? You're standing up. It's as if there's there's no motion at all. You don't really notice it. All right. Now this is on the mythical, highly mythical, smooth roadway, and without a maniac at the wheel of the shuttle bus. Does anybody here work for the shuttle bus company? Okay, good. Well, I'll just reveal my opinion about them. They're maniacs, most of them. Did you ever notice how they drive? It's like they're jerking the thing around and just definitely not uniform speed and velocity. But now, if the car speed, if the bus moves up, you move backwards, or you seem to lurch backwards. It's like your feet are taken out from under you. Okay, so you have to stabilize. That's why they have all those bars on a shuttle bus, so you can stabilize yourself as you go up and down that row. Now down here, same thing. If you're in the shuttle bus and it's going straight south at 5 miles an hour and takes a right turn to go not down towards Research Park but over towards the gym, the rec center, right? All right, takes a right turn. You're gonna keep going in the same direction. So for you, it's going to feel like you're going to bump your left hip. If it goes right, you want to keep going straight, which in terms of the bus means you're going to feel like a leftward push. You're going to bump your hip on the left side. All right. So that's an example of you, because you're not nailed down, you're not screwed and bolted down to the bus. All the seats are. Can you imagine a bus, especially one of our shuttle buses, where the seats were not bolted down? Oh my goodness. Talk about mayhem. With the way and with the roads as bumpy as ours are, and those drivers, oh my goodness. But if if the seats are bolted down, then they go with the bus, but you don't have to, unless you stabilize yourself fore and aft, port and starboard. All right, then you can stay with the bus. Otherwise, you're going to take a spill. Unless your bus never changes its state of motion, but if that's the case, then you're off. It's like the permanent home run out in space. You're just going to keep on going. All right, so we don't have any shuttle buses like that. All right, so this is the law where you have to stabilize yourself in the aisle of a bus and stuff like that. Anytime you turn in a car, that's an accelerated system, making a turn. And here's another thing Galileo said, and this is also related to the Ferrari driving off a cliff problem. he said that those two motions are separate. You know what it does vertically, up and down, and what it does left to right up on the frictionless plane, those are separate. Those are separable. You know, you can analyze one of them separately. All right? And we've already done that with the y equation, for the y coordinate. We've got the initial value of the upward velocity, and then we've got g, but we don't have any horizontal information in there. In the formula for x, we have the initial value of the horizontal velocity, and that's all we got. We don't have any accelerations. Okay, and so they separate. Now, one factor or one way to look at that is to look at the components. So this is a football, a quarterback throwing a football to a wide receiver. And if you look at the light blue arrows, which are a little tough to see on the screen maybe, you'll notice that the vertical ones start big, get smaller, and up here at the top, they're zip-zap. That's the top of the motion where you've lost all your upward speed. And then you gain it back on the way back down towards the wide receiver here. All right? But notice the horizontal part. Now, I'm going to use this little red arrow, this little sparkly red arrow here right now. This arrow, there it is. Okay? It's the same size for all these strobe photos every instant. Now, here it is up here at the top of the motion, what we call apogee. Same, and that's all the velocity you've got up there. You only have sideways velocity. You never lose it, and up there at the top, that's all you got because you've lost your vertical. But see, now down here, you're starting to gain your vertical back, except it's downward vertical. So that's all right. That's what gravity does. It's always trying to make you fall. It's always trying to suck you in. Gravity sucks, they say. All right, so here's another one. So this sideways arrows, the horizontal arrows of velocity components, always the same size. All right, because there's no such thing as horizontal gravity. All right, so those arrows, same, ditto, 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 all the way across. No matter how many snapshots you get, it's dittos all the way across. Now, the vertical parts, plenty of change. Okay? G delta T. That's your change in velocity for the upward part of the velocity. All right? Now, let's do some clicking. Make sure you have your clicker on, if you please. And this one is going to be multiple. Actually, this one's going to be multiple choice. And so let's just do a couple thinking questions here. Just think about this one. This blue car moves to the right at constant speed. So which one of those statements is correct? Hit your refresh button, and all you have to do is click in a letter with the 5-letter keys. Read carefully. With my exams and my clicker questions, always read carefully. Don't go too fast. And I'm looking to see if anybody's tried to vote for option F. Anybody see a problem with option F? Well, there is no F, but if there were, what's wrong with it? All of the above includes none of the above. So what exactly is F? I actually did that on an astronomy exam once. My TA caught it. I was pretty embarrassed. Because your test bank software scrambles the answers, and so it was all messed up. Okay, 10 seconds to vote. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Yeah, this is the correct answer. It's constant. Yeah, constant velocity, constant speed, and it's moving to the right. So there's a constant direction, moving to the right, and constant speed. Ding, that means constant velocity. All right, now we're doing a lot of thinking about concepts here. Let's go to the next. So this is here's an example. So your velocity vector is straight rightward, v subscript I, at some speed like 10.5 meters per second. Okay, so that's for example. You know, now that would be 20 something miles per hour. So that's just kind of poking around campus in your car. All right, and hopefully your car is better than the shuttle bus service. Now, next question, multiple choice. You observe a can of Pepsi. You observe a clicker on a tabletop. See, nobody's talking to Anna, but these other two students are talking to Yaz. Nice. So if you want to study with Anna, come up here in front. Next time, just make yourself at home. Okay, 20 seconds to vote, starting now. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Sorry, I had to yawn there. Okay, can of Pepsi. Let's look at this. Actually, let me look at your guys. Oh. We got some splaining to do because is it A, is it B, or is it C? So there seems to be a split of opinion here. So let's look at these babies. Okay, A, no force is acting. Is there a force acting on the soda pop can? What? Gravity for sure. So A is out. B, it has more than one vertical force acting on it. What's the other force? So the what? Yeah, the rigidity force from the table. Okay, so there's two. All right, so B is possible. C, it has only one vertical. Okay, so that one's out. So C is out. We just proved that. It has only horizontal forces acting on it. No, it doesn't have any horizontal forces. It's just sitting there. It only has verticals, and there's two of them. So B is the correct answer. Now go ahead and make a sketch of a can of Pepsi on top of a tabletop, and let's just add in a couple arrows to represent those two balanced forces. There they are. So the idea here is that if you say something is at rest or constant velocity, there's no acceleration. And that means you might have no forces, or you might have no unbalanced forces. In other words, you might have everything balancing, which is the case with the soda pop can. And believe it or not, my wonderful students, this particular question, I've seen grad students, physics grad students, get turned around, they don't know which way is up. In grad school, if you're going for a PhD, you write a thesis or a dissertation, and then you defend it. And in the grad school where I was at Montana State, when you defend your thesis, you have a committee of faculty, and they pepper you with questions about your thesis. And then when that's finished, then it's open. They can ask you any question. And one of the guys in our department asked this question. So this poor guy, Nick Pinto, was up there. He just defended some very fancy quantum mechanics thesis, right? And so the professor puts his can of Pepsi up on the overhead projector, up there in the front, and says, "Okay, diagram the forces on this can of Pepsi." And so he proceeded to, and this guy that semester was teaching a class like this. So he was used to, asking questions and stuff and guiding people. So he was peppering up Nick Pinto with questions, and by the time Nick was done, he didn't know which way was up, but they still passed him, and he's now a doctor. God bless him, Nick Pinto. But this is a famous question. So as I said before, you guys are getting concepts that are new for you, and they may seem difficult, and they are. And that is the difficult part of all of physics. Einstein said, if we knew what we were doing, it would not be called research. All right? Now, he knows all about this stuff because he's already learned it. But in the day of Galileo, this was all, and Sir Isaac Newton, this was all new thinking. All right? And you could still, catch an odd grad student with the right question on it. Now, let's go to the second law, and then we'll finish with this. And then we'll dismiss. So the first law says, okay, you're at rest, either no force, you're at rest or constant velocity, and there's either no forces or no unbalanced forces. You got some forces, but they all balance. Now, the second law says, all right, what happens if they're unbalanced forces? You're going to get acceleration. All right? So he said what you do is you add up all the forces. All right? And if anything doesn't balance, you have a little bit more to the right than you do to the left, then that's your net force. All right? And that's denoted capital F with a subscript NET, net force. All right? So here's an example. Dwight Howard versus LeBron James. They're on the same team now, but so let's say that Dwight Howard pulls with 100 units of force to the right, and LeBron James only has 80 units of force to the left. So his force is negatory, and the negative sign here means, Brad, the negative sign here means leftward. Okay, all right. So that means you got 20 units leftovers. So that's your net force. And it's in the Dwight Howard direction. So Dwight Howard has 20 more that don't balance that LeBron James cannot balance. So he wins. Okay? And so that's the way that the acceleration goes. So Dwight Howard gets the ball. Now, so that's the first part. How do you get the net force? Then the next thing you do is you add this concept. The more push or pull force you have, the more acceleration. Right? That makes sense. So if you have a little first grader pushing a loaded grocery cart and Arnold Schwarzenegger pushing the same grocery cart, Arnold's going to have a lot more acceleration than the little shrimpy first grader. Okay? So that's kind of what this is about. Now the third concept is the more kilograms of mass you have, the harder it is to accelerate it. So that means if you have Arnold or anybody and you have a lightly loaded grocery cart and you have a totally loaded grocery cart with canned goods, really heavy, then it's going to be harder to accelerate the loaded one because it has more kilograms of mass. All right? And so the way that we write that as in an equation form is this. Acceleration is the quotient of net force and total mass. A equals F net over M. And another way to write that is simply by cross multiplying. F net equals MA. That's another way that you sometimes see people write it. And guys over in the engineering department have a large area of their brain dedicated to this formula. F equals MA, Newton's second. This is Newton's second law. And so if you have an annoying friend, a friend that's an engineering major and they're really annoying, all you have to do is go up to them while they're doing their homework, and they're up there with the calculator and the colored pens, the graph pen, all their fan, and they're thinking, yeah, man, I'm so hot. I know how to do all this junk. And you just go up behind them and put your hand on their shoulder and say, oh yeah, F equals MA. And you'll totally fry their brains because they'll think, how the heck did they figure that out? Just by looking at my homework. And you'll never be wrong, right? F equals MA rules the cosmos. So yeah, just keep that in mind if you feel like annoying an engineering major, which is always a um, fun practice. All right, we're gonna stop right here. You have enough now. Let me go all the way to the homework page. You have enough now for homework 2. I also want you to finish reading chapter 2 and start skimming forward through chapter 3. Okay? And we'll be talking about that next week. Okay, you're dismissed. 2 minutes early.